And last but not least, we have Daxun to be our last speaker. He's from University of Buffalo, and he will be telling us about on the classification of generalized Baumslag-Solitar groups. Please.
Okay. Thank you for the invitation. It's an honor to speak at this conference. So I want to talk about this classification of generalized Baumslag-Solitar groups. So first, let me give you an example of what is this generalized Baumslag-Solitar groups are. So suppose we have a circle that looks like this. So next, I want to multiply the circle with a closed interval. So this will give us a cylinder that looks like this. And next, I want to glue this cylinder together, but not in the trivial way, because in the trivial way we will get a torus. But this time, we want to glue these two circles together, but not the trivial way. So for the circle on the left, we want to twist it n times. And for this circle on the right, we want to twist it n times. And then we glue these two circles together. So after that, we can obtain a topological space that looks like a torus, but not the actual torus here. And we name this topological space, let's say K. So in fact, we can write the presentation of this fundamental group of this topological space K. So the fundamental group of this K, it has two generators, X and T, where this X is actually represent this circle here, these two circles here. And this T is actually represented by this circle after the gluing part. And also it has the relation, it looks like T x to the m, T inverse equals to x to the n. So this is actually the presentation of the fundamental group of this topological space K. And this group here is what we call the Baumslag-Solitar groups. And we denote it by BSMN. So this Baumslag-Solitar groups is actually an example of this generalized Baumslag-Solitar groups. Yeah. So far, any question? Okay. So before I introduce this generalized Baumslag-Solitar groups, I want to talk about this graph of groups. So this graph of groups structure contains two parts. The first part, it contains a graph gamma, and this gamma contains vertices and oriented edges. So for example, this gamma could be just a simple edge. It has two vertices, V and W. And we have edge E that pointing to the right. So let's say this is our E here, because we need the edges to be like oriented edges. And associated to this edge E, we have its inverse orientation. So we have this E bar here that pointing to the left. And also we have a system of groups. For every vertex V, we associate it with a vertex group G sub V. And for every edge, we associate with an edge group G sub E, such that just G sub E equals to G sub E bar. So we require that the edge group isomorphic to the edge group of its inverse orientation. And based on these two groups, we have an injection for every edge, this alpha E, where we map each edge group to its initial vertex group. So this is actually the definition of this graph of groups. So I want to give you an example of what of this graph of groups. So suppose we have our graph gamma looks like this. It's just a loop with one vertex v. So for this vertex v, we associate with the vertex group GV. And let's say our GV is infinite cyclic. So it's just C. And let's denote the generator of this group to be X. So this is our GV here. And for the edge group, just G sub E, we associate with a edge group, G sub E. So let's say it's still infinite cyclic. And we define its generator to be Y. So based on our definition of this graph of groups, we require that this GE isomorphic to G sub E bar. And we have two injection map because we have two oriented edges. For this alpha, oriented edge E, we have alpha E that maps this GE into GV. And we maps this Y to, let's say, X to the M. So this is actually an injection map. And we have another injection map for this oriented edge E bar. We have alpha E bar that maps GE bar into its initial vertex, so it's still GV. And this time, it maps Y to, let's say, X to the N. So this is actually a valid graph of groups structure here, because we have our graph and we have a system of groups and injection maps. So the reason this graph of groups structure is very important because if you look at our example here, this graph of group structure can be realized by this example here. How to realize this? Let's say the method is like this. So for every vertex we want to construct a topological space KV such that the fundamental group of this KV isomorphic to the vertex group. So in our case, our vertex group is infinite cyclic. So this KV is just a circle here. And for every edge, we want to construct a space KE cross I, where the fundamental group of the space KE is isomorphic to the edge group. So since in our case, the edge group is still infinite cyclic, so our KE is still a circle. And this KE cross I is just a circle, it's just a cylinder. So what does this two injection maps do? These two injection maps actually tells us how to glue this KV and this cylinder together. So in this example, this injection map actually means that we twist this circle m times. So here, this is we twist m times. And this injection map here actually means that we twist this circle n times. And then we glue this cylinder together. And after that, we can get the topological space K. And as we can see, this topological space is just our topological space here, because this is how we glue these two things together. Yeah. And we define the fundamental group of graph of groups, this pi1 gamma G, to be the fundamental group of our topological space K. And in this example, this fundamental group is just the Baumslag-Solitar groups. So it's just BSMN. So far, any question? Okay. So by this graph of group structure, this is equivalent to say that our Baumslag-Solitar group has a graph of groups decomposition where every vertex and edge group is infinitely cyclic, because in our example here, the vertex group is infinitely cyclic and the edge group is also infinitely cyclic. So here comes the actual definition of this generalized Baumslag-Solitar groups. A group is a generalized Baumslag-Solitar group if and only if it can be decomposed as a graph of infinite cyclic groups. So this actually means every GBS group admits a graph of groups decomposition where each vertex and edge group is isomorphic to Z. Okay. So let me give you another example of this GBS group. So let's say our graph of groups structure looks like just instead of a loop, we have a simple edge. It has two vertices V and W, and we have an oriented edge E pointing to the right. So to make this this group to be a GBS group, we need the vertex group and the edge group to be infinite cyclic. So this GV here should be isomorphic to Z, and GE is also isomorphic to Z. GW should be also isomorphic to Z. And let's name the generator of these three groups. So let's say this is X, generated by X, GE is generated by T, and GW is generated by Y. So for this graph of groups structure, we need the injection map for each oriented edge. So for this alpha E, it actually maps this T, this infinite cyclic group generated by T into GV. This is alpha E here. And the alpha E bar is really just we map this this GE into GW. So this is alpha E bar. And what is exactly this this injection map? So let's say we map this T to X to the power P, and for this alpha E bar, we map this T to X to the power Q for some integers P and Q. So this is actually another example of this graph of groups structure. And the fundamental group of this graph of groups is just the torus knot group. So it's actually generated by X and Y, and the relation is X to the P equals to Y. Oh, sorry, this should be Y here. Y to the power Q. So this is the torus knot group. So this is actually another example of this generalized Baumslag-Solitar groups. Okay, so the next part I want to talk about the isomorphism problem of this GBS groups. By isomorphism problem, it really means that we need an algorithm to determine whether two GBS groups are isomorphic. So if you look at our example here, it's very hard to visualize what this GBS group looks like by just look at this graph of groups structure. So we have a better tool to visualize each GBS group is called the labeled graph. And this is introduced by Max Forrester and Matt Clay, and also used by Vincent Gradio and Gilbert Levy in their paper. So what does this labeled graph looks like? So because according to the definition of this GBS group, every vertex stabilizer, every vertex group is isomorphic to Z, and every edge group still isomorphic to Z. So our injection map alpha E is actually, we map Z into Z. So if you choose the right generator here, this injection map is actually just a multiplication of an integer. So let's say for this example here, for this map, we can identify this infinite cyclic group as x to the power p, and it actually maps into the infinite cyclic group generated by x. So as you can see, this injection map is really, we multiply the exponent by p. And for this alpha E bar, we can identify this infinite cyclic group as y to the power q. So in that case, it actually maps this y to the power, this infinite cyclic group generated by y to the power q into y. So it's, the map is really just we multiply the exponent by q. So for each edge, it actually carries two labels that are integers. So this is actually the what is this labeled graph looks like. So for this second example here, we have our graph of groups structure like this. So the inclusion map here is multiplied by P, here is multiplied by Q. So our labeled graph is just a simple edge that carries two labels P and Q. And for the first example here, this example here, we have the inclusion map. We can identify this G sub E by the group generated by x to the m. So it maps into the group generated by x. So it's just a multiplication by m. And here, the same way, this alpha E bar is just the multiplication by n. So in that case, in the first example, the graph of group structure is here is multiplication by m, here is multiplication by n. So the labeled graph is just as a loop that has two labels, m and n. So this is actually a much more clear way to visualize each GBS group. For this labeled graph, I want to mention two things. So first, each GBS group can have infinitely many labeled graphs. This is because if you change the presentation of a GBS group, you have a different graph of groups decomposition. So you will get a different labeled graph. But the nice way of this labeled graph is actually that we turn this isomorphism problem of this GBS group into the isomorphism problem of labeled graphs. So this is a much more clear way to approach this isomorphism problem. So next, I want to talk about the current results of this isomorphism problem. So there is a very useful theorem introduced by Max Forrester and Matt Clay in 2007. This theorem said any two reduced labeled graphs representing the same GBS group are related by a finite sequence of moves of this labeled graphs. So let me give you an example of this moves here. So suppose we have a labeled graph looks like this. We have an edge, we have two edges. The label for, let me change the color. The label for this blue edge is M and N, and the label for this green edge here is L times M. Both L and N are integers. So in this case, we can just slide this green edge over the blue edge to here, like this. This blue edge is still here, but the green edge is attached to this vertex. And we change the label instead of L times N, L times M, here is L times N. So this is kind of special moves, a special move of labeled graph. And this, you can check that this doesn't change the ambient GBS group. So it's actually, we turn this labeled graph into another isomorphic labeled graphs. And this is what we call the slide moves. There are still two more moves, but because of the short time, so I just mentioned this one. If you're interested, you can just look at their paper in 2007. There are another two more moves about this labeled graphs. So the reason why this theorem is very useful, because for given two labeled graph that representing the same GBS group, we know how to change from one to the other by using this three moves here. And next, this is a theorem by Gilbert Levin in 2007. He solved the isomorphism problem of the GBS group, where the outer automorphism of the group is virtually nilpotent. And there's another result by Max Forrester and Matt Clay in 2009. They solved the isomorphism problem of GBS group, whose labeled graph have first Belly number at most 1. So this first Belly number actually means that how many loops in how many cycles. This first Belly number is actually the number of cycles in your labeled graph. So in this case, because the first Belly number at most 1, so you can only have at most 1 loop. So your labeled graph is just some trees, or you can have some loop here, but you can only have 1 loop. Okay, so this is some current results of this isomorphism problem of this GBS group. So my idea to approach this problem is actually we can divide this GBS group into 2 separate parts, the ascending part and the non-ascending part. So the ascending part means that among all labeled graphs that representing this GBS group G, there exists a labeled graph gamma such that it contains a special oriented cycle. The definition for this special oriented cycle is very complicated, so I don't introduce the actual definition here. But this is actually in the graph. This is actually just an oriented cycle with some other properties here. So this is the definition for this ascending. And next, because we divide this GBS groups into 2 parts, so to approach the isomorphism problem, we can divide into these 3 steps. So first, we can determine when a GBS group G is ascending. But to approach this, first we need to determine whether a given labeled graph contains a spatial oriented cycle. If it contains a spatial oriented cycle, then our group G is ascending. If it doesn't, then we need to check all the other labeled graph whether there exists as a labeled graph that contains a spatial oriented cycle. So far, I think I have this algorithm for this spatial oriented cycle, and for the last step of this ascending part, I'm stuck at the last step proof, but I think it's still approachable for this algorithm here. So once we have this algorithm to determine whether a GBS group is ascending, then we can divide this into two parts, the non-ascending case and the ascending case. So for each separate part, we can define the normal form of labeled graph. And for and the isomorphism problem is really just for two given labeled graph, we can change the labeled graphs into its normal forms, and we compare the normal form. If they are isomorphic, then it is the group isomorphic. So so far I'm still still searching the algorithm for this normal form, but still I think it's approachable so far. Okay, so I want to save time. Save some time for questions, and thank you. That's it. Yeah.
Now let's thank the speaker. Any questions for the speaker?
So what kind of normal form is it?
The normal form is just a special labeled graph that representing this G. So it's like for each group we may have like infinite many labeled graph, and we pick a finite set of this labeled graph that has certain properties, and we name it normal form. So for any group, we can just compare these two finite sets, and if they are like they have intersection, then the group are isomorphic. Does this answer your question?
Okay. So you're searching for a good normal form there, or?
Yeah.
Okay. Thanks.
Yeah.
Any other questions? So when you say you're solving the isomorphism problem, you mean you have a computer algorithm, right? So it's computable.
Yeah, it's computable.
Okay. And here when you say ascending, does it have any relation to, because for the usual Baumslag-Solitar groups, you can think of it as an HN extension. Does that have any relation to whether the HN extension is ascending or no?
The HN for this Baumslag-Solitar group here, if this M or N is 1, then it's ascending. But right. If it's some integers, then it may not be ascending. So far right now we don't have it. Yeah. So
it's kind of related to, because in the regular Baumslag-Solitar group, if one of them is 1, then it's if and only if it's solvable, right? So does it have some relation there? Like in general, if you're ascending, then the generalized Baumslag-Solitar group is solvable, maybe, or?
So far, I don't know that. Sorry. Okay. Let me check that and let you know. Yeah.
Okay. All right. Thank you very much.
Yeah, no problem.
Any other questions? All right. If not, let's thank the speaker again.